Hey everyone, today we're going to talk more about limits and different types of asymptotes, vertical asymptotes and horizontal asymptotes. So in the work we were doing previously, we were talking about limits to infinity as x approaches infinity, and we talked a little bit about horizontal asymptotes, and we talked about how both the positive and the negative direction were the same, right? And that happens when you have a rational function. However, there are situations where we have other two types of functions, and that's a quotient. They're not necessarily rational functions because it's not a polynomial divided by a polynomial, but it might just be a quotient of two other types of functions. And these may even create more than one horizontal asymptote. So generally, as a rule, we say when we have two functions that are divided, if the denominator grows faster than the numerator, then the limit as x approaches infinity will be 0. If the numerator grows faster, you see that's in quotations, then the denominator, then that limit will increase or decrease without bound. If they grow at the same rate, then the limit will be a constant value. A lot of wording in there, so let me explain to you through some examples what I mean by that. If you look at this graphic over here on the right, this is telling you the order in which they grow. So constants grow at the slowest rate, but factorial expressions or factorial functions grow at the fastest rate. Okay, so the top of the list is fastest, and as you go down the list, they grow at a slower and slower rate, right? So that's why the arrow is pointing down. As you go down the list, the growth rate slows down. So let's go through a few examples here. If we look at this example A, it says the limit as x goes to infinity of sine x over x. So this is not a rational function because it's not a polynomial divided by a polynomial. So we can't use any of those rules we talked about previously. But what we need to do is determine whether or not the numerator is growing faster than the denominator. So what I'm going to do is I'm going to go over to my handy little chart here. Okay, so I've got sine x, which falls right here on my chart. So this is my sine x function, and the bottom one is just has some sort of x, whether it's x squared, 2x squared plus 1, 3x cubed minus 4x plus 7, anything like that would be a polynomial function, right? So this is polynomial. And so if you look at the comparison along this growth rate chart, polynomial grows faster than sine. So my denominator is growing faster than my top. So my bottom grows faster. Because my bottom grows faster, I can say then that the limit as x goes to infinity of sine x over x is going to equal 0. If the bottom grows faster than the numerator, it approaches 0. Okay, so that's one example. Let's look at the second example, letter B here. We've got x going to negative infinity. In this case, we don't have a polynomial function. We have a combination of different functions, and it's actually not even one divided by the other, so it might seem kind of confusing how we're going to approach this. So let's look at each part separately, right? This right here is exponential, right? E to the x. Anything with a variable in the exponent is exponential, okay? And this would be polynomial. So exponential is going to grow faster than the polynomial. So this is the one we're going to be most concerned with. So we can really just look at this as limit as x goes to negative infinity of e to the x. Okay, so if I were to substitute negative infinity in for x, right, I would have e to the negative infinity. Remember that a negative exponent takes something from the numerator and puts it in the denominator. So now I do have this idea of something divided by something else, right? So my numerator is a constant. My denominator is exponential. So my denominator is going to grow faster. So since the bottom grows faster, I can then say the limit as x goes to negative infinity of e to the x minus 2x is going to be 0. So once again, I started with what I had. The exponential part grows faster than the polynomial part. So that's the one I'm going to focus on because that's the one that's going to determine what's happening to the overall function. And then I just worked with that and I said, okay, well, let's go ahead and do a direct substitution. A negative exponent takes something from the numerator and puts it in the denominator. And now I have this idea of a constant over an exponential. And the exponential grows faster than the constant. Okay, let's look at a few more examples. In this case, I've got x going to infinity, and I have this and this, right? So I have exponential over exponential. Okay, so what does that do? If I have exponential over exponential, I'm going to have to look at those separately, right? These two are going to determine what happens to this whole function. And so if I just really look at 2 to the x over negative 2 to the x, remember my limit is going to infinity, so I can use that whole idea of an end behavior model. And I can say, okay, well, let me look at what's going on here, right? These constants, that's not going to change. This is where everything is happening. If I were to simplify that, right, 2 over negative 2, that's just going to be negative 1, right? Because this is the same as 2 to the x over negative 1 times 2 to the x. Anything divided by itself is just 1. So that whole expression reduces to negative 1. And because of that then, right, my limit to infinity is just approaching, let me rewrite the original problem, 5 plus 2 to the x over 2 minus 2 to the x. Because I'm approaching this constant value, it doesn't matter what infinity, it doesn't matter that x is going to infinity, I'm approaching this constant, so my limit here is negative 1. Now, a lot of people would look at C and D and go, well, it's the exact same thing. In this case, it's just going to negative infinity. In that case, it went to positive infinity. So this should probably also be just negative 1. Or sometimes people say, well, if positive infinity went to negative 1, then negative infinity is going to go to positive 1. Okay, and you cannot do that. You cannot make that assumption. So if we were to look at this, again, we can look at what's happening here with these values here, right? So think about what's happening. I'm putting in to the negative infinity. Okay, if I have 2 to the negative infinity, that's the same as 1 over 2 to the positive infinity. So I have a constant over something that is going to infinity. So that is going to go closer and closer to 0. So both the top and the bottom, those two pieces approach 0. Approach 0. Okay, so in essence, I end up with the limit as x is going to negative infinity of 5 plus 0 over 2 minus 0. Well, that was just going to give you then 5 halves. So again, look at what's going on here. 2 to the infinity, in letter C, 2 to the infinity gets closer and closer to infinity. Okay? Negative 2 to the infinity gets closer and closer to negative infinity. So these, basically the 5 and the 2 become just insignificant because I'm going to positive infinity in the top, negative infinity in the bottom, and that's what creates that negative 1. The difference here is because it's going to negative infinity, I have 2 to the negative infinity, which would be 1 over 2 to the positive infinity. And that, because my numerator is, my denominator is growing faster than my numerator, that's approaching 0. So this component and this component are both approaching 0, which leaves me with just 5 over 2 as my limit. Okay, so they look like they should be the same, but you're looking at different parts of it because of the fact that one's going to positive infinity, and in the second example, it's going to negative infinity. Okay, let's look at a second type. The second type of problem we have is when we have infinite limits as x approaches some value. So in this case, I'm approaching 0. And the graph of this, if this is my axes, the graph of this, we talked about this before, it basically looks like this. Okay, that's the graph. So if I'm approaching if I'm approaching 0 from the left, I'm going this way. Right, this is x approaching 0 from the left. And as I'm getting closer and closer to 0, my function is heading this way. It's heading towards negative infinity. So this limit is going to be negative infinity. Over here, part B, as I'm approaching 0 from the right, I'm going this way. So this is x approaching 0 from the right, and you'll notice I'm going here, I'm going to positive infinity. So here, I'm just approaching positive infinity. And so what we would say overall is that the limit, as x approaches 0 of 1 over x, we would say it does not exist because the limit as x approaches 0 from the left of 1 over x does not equal the limit as x approaches 0 from the right of 1 over x. If the limits from both sides are not the same, then we have to conclude that the limit doesn't exist. And that's when you end up with a vertical asymptote. So here's the idea. At a vertical asymptote, either the limit from the left and the limit from the right are going to approach the same. They're either both going to approach positive infinity or they're both going to approach negative infinity, or one is going to approach positive and one is going to approach negative. In the event that one approaches positive infinity and one approaches negative infinity, overall we say our limit does not exist. Okay, and that's the idea behind what a vertical asymptote is. Okay, so as we approach that letter A or that number from the left or the right, we're approaching either positive or negative infinity. Okay? This note says that this occurs whenever there's a value of x that gives you 0 in the denominator but not the numerator. And we're going to go through some examples. If the value of x gives you 0 in both the numerator and denominator, then that graph has a hole. Okay, so we'll talk about that as well. So I'm going to stop this video here. I'm going to pick up in the next video with some examples. All right, thanks everyone.